Hello everyone, welcome to EDSIL. In this video, we are going to discuss about the approximation algorithm introduction. So basically, which we have already discussed about the tractability and intractability model, or you can say the problems, which we have already discussed. Those who are new, kindly check out the previous videos where we discussed about NP hard, NP complete, NP as well as P, what exactly the P space is all about. That we have already completed. Kindly watch that video before watching this approximation. So here we are basically working for the NP complete problems. Okay, as we have already completed that one, I'm just giving you the just a view of NP complete, what it is exactly. Okay, so between NP and NP hard, there is a problem lies in between. Like as we have already discussed earlier, like NP complete is just harder than the NP, but less hard than the NP hard. Okay, so like it's a basically a, you can say a decision kind of problem where yes or no conditions are there in NP and co-NP, which we earlier discussed. If you are finding, if you have verified, like the verification of answers, like we have also taken the example. I must tell you that one. Uh, you can think of like uh, just consider a puzzle. Okay, puzzle or jigsaw puzzle problem. There we know the pieces are in a scattered format suppose given to you. If you want to just try to connect all the jigsaw puzzle pieces and you just want to make a whole puzzle might be completed, that time it will take time to add every pieces into a single piece. If certain thing like to add it, it is taking time. Once it is getting added, okay, just want to verify what exactly the output is and what you formed with that. Okay, like if you want to verify that one, definitely verification is taking a polynomial time. Means verifiable is possible, verification is possible. If yes, we can do the verification that we discussed as it's a part of NP. Co-NP is a complement to NP. Like if you can say no, not it is not possible. Like you can verify it that one. So that we have already discussed. Some problem are there which have certain solution, but still it takes time or more. Complexity is more, or some case like we it's somehow hard than the NP which we have already completed. Like we have certain range of that one, like that is a part of NP complete. Okay, or NPC, sometimes we say NPC or NP hyphen C or NPC, we can write in that way. Okay, certain problems are like NP complete, like we have already completed about sort during our reducibility. Those who are new, again I'm telling you, please watch the previous videos related to the reductions and everything. Okay, so basically this content approximation as well as other contents which I am collecting from the book, Corman book, as well as the Tardos book, okay, which is the textbook nowadays are following in universities, different universities. They are following the Corman book, as well as some universities are following Tardos book as a textbook. There I'm following Corman sometimes. So here for this approximation introduction, I'm following Corman book, which is named as Introduction to Algorithm. There you can find out this content, but it is not that much easy to understand directly if you're just reading the book. For reading the book, it is always, you should remember, you should have some prior knowledge. You should have to surf from the internet, then you go to read the books. It will be very easy to understand. Okay, so now coming to the topic, NPC and NP hard, basically we cannot do easy solutions for NP hard. Somehow we have certain expectations for NP complete. That's why certain problems, though we try to reduce those problems with towards P, or might be you can say it's easy to find a solution. Not about a polynomial or anything. It's really easy to find a solution. That's why we have produced, or we have certain way to say approximation that we'll discuss now. Okay, like though our topic is first line I have written here is about the NP complete. Certain NP complete, there is a hope to find a solution for NP complete. Okay, so what exactly, how to avoid that NP complete basically? There are three steps I have collected from the book. So here the first what exactly we can do, either we can, the input size if it is more, so definitely the complexity will be more that we know. Okay, if we less the input size, okay, means you can say those who are in data science that like if your sample space is too small, you can distinguish what the type of data is. Okay, so if a sample space is large, if our data is large, definitely it will take more time to find the background details, or to find the about the data exactly. Okay, so first step is we can take the input size as small. Second is able to isolate important special cases. We can at least compromises with some features of it, or what exactly the data is already available by the input space. There we can do certain isolation of important special cases. Through that we can have to avoid the NP complete. So another portion way is we might come with an approach which is providing the near optimal solutions in polynomial time. Okay, basically we targeted towards a polynomial time. Why? Because it's going to be reduced. By the way, I'm just again recalling that one. A reduction is all about, like, if it is easy to understood, by any sense. Suppose your mother tongue is different. You don't know the English. Okay, English is not your mother tongue. Suppose your mother tongue could be Hindi or any other language. Okay, your own native language. Once you are reading a book which is written in English, simple English, what exactly you're doing, you may not might be thought for, but always you should, whenever you're reading English, the first step is you are reducing to your own language. Okay, always. Own means your native language. I'm saying that one as your native language. You are converting, because the native language is giving you the feelings about what exactly it is written, because it is not, English is not your mother tongue or not your native language. So that's why what exactly it is written somewhere, it is just a high level language for you to understand. While you are understanding it, while you are knowing it, that time you are reducing to your own language. Once it is understood, this is what your solution is, and this is a reduction. Okay, this is reduction. Sometimes what happened, like whenever we are doing a reduction, like some English word is, somehow you think the word is similar to your own languages, suppose anything. So if it is similar when we are saying it is similar means approximately you are taking the answer. It's not always correct in approximation, as whenever we are doing in mathematics. Okay, we have taken approximation, that time we are indirectly saying the approximation is similarly equal to, this is not equal to. Similarly equal to, sometimes we are writing in mathematics, the similarly equal to is exactly giving us the way to say approximation. Sometimes we are saying 1.5 is equal to 2. No, it is not equal to 2. It is, we are writing similarly equal to 2, because that time we are just writing floor function or ceiling function. For this, suppose I am just writing it is 2, so I have to take this as ceiling function of it, then only I can say it is 2. But it is also written as similarly equal to, nearly equal to. Okay, if I am interested to write 1.5 is equal to 1, I must have to write this. But zero point 0.5, why to reduce them? There is an approximation concept we have introduced. So third point, it is written, we can find an approach through which we can get a near optimal solution. Near optimal solution, not exactly the optimal solution we are getting. We are somehow equivalent to near optimal. Suppose optimal solution you need to find as 2. Instead of getting 2, you might be getting 2.5. The 2.5 is our approximation algorithm then. It is not optimal, this is optimal for us. Why optimal I'm using? Because in NP complete, different type of problems are there. Here in other, next videos we are going to discuss about the practicality of the approximation, which we have discussed in the introduction video. So this introduction video is all about like what is approximation, what are the type of approximation schemes are there, like how we can introduce approximation. That is about the introduction video. And then upcoming videos we are going to discuss about the application of it, like vortex cover, or you can say traveling salesman problem. Every approximation problems are there. Even if load balancing also we can discuss about max span, everything we'll discuss that one the next videos. So here the first target is we are not getting 2 as an optimal solution. Optimal means, suppose I'm just giving one graph, A to B, then B to C. So here from another point D, we are reaching towards C. It's not a direct example I'm saying. I'm just saying an example. Okay. So here it is 1. Here it is again 1. Uh, Here it is 2. Here it is 1. Here it is 5. And here 2. Here it is 2. So whenever we are finding the source, this is our source, this is our destination. Whenever we are finding the distance from A to C, there are 3 different ways we can pick. Try to understand. This is just an example I'm just giving. So to find the optimal solution means the shortest path from A to C, the shortest path is 2 plus 1, which is 3. That we know it is the shortest path. But if you just used your greedy approach, just take this as an example of our study here. Okay. Out of this, as for the greedy approach, shortest will be picked first. So 1, then 5, it is 6. Another approach, suppose you take not DP, not greedy, just a brute force approach. You think, no, I'll start from E. Go for it. You can start from E to C, then it will be 2 plus 2 is 4. 6 is not nearly optimal to 3, but 4 is somehow nearly equivalent to 3. In that case, I must tell you this 4, this line, this from A to C through E is optimal and approximation solutions, which is nearly optimal to our problem. Okay, this is what the example, through example we can understand like how it really helpful for us to understand. And one more thing I must tell you, this is not about any problem, this is all about the NP complete problem. In other videos, like in upcoming videos, we are going to definitely discuss about how the vertex cover is exactly being planned, how we are getting an approximation algorithm, how we are getting with the optimal solutions. Everything we'll discuss that one. So here it is written like near optimality is often good enough. Okay, as compared to these 3 different points which we discussed. Out of these 3, we think we do not want to, we will never guarantee about the input size, because it might be n is, like it is not yet defined. N could be 10, n could be 20, n could be anything. So n could not be small. And here also we cannot, even if segregate, or you cannot compromise with the number of inputs basically. So your optimal solution somehow the easiest solution for us. That's why we are trying to say the uh, the third one is our approximation algorithm. That's why approximation algorithm is getting introduced. Okay. So I hope you understood like why approximation algorithm is introduced. Now, like approximation algorithm, whenever we discussed about that one, the find the optimal solutions basically, that type of, to find that one is maximum possible cost we can expect, or a minimum possible cost we can expect. Okay, in that case also, if you're getting maximum possible cost, that is called as maximizations, or a minimum possible cost, suppose you are getting as minimization problem. Don't worry about that one, we will discuss one by one. Okay, so there is a formula where we say maximum, just you can say maximum is a function we have used. where c by c star comma c star by c. If it is, whatever the maximum that you are getting, if it is less than equal to rho of n, we must say rho. What is rho and what is this, we are going to now discuss. C is a solution produced or a cost produced by solution, or you can say it's a cost produced by the algorithm. Which algorithm? Is the approximation algorithm which you have taken already. Okay, this is about the approximation algorithm which is generated by the approximation algorithm. Okay, so don't worry about, because this is an introduction. Definitely whenever we will discuss about the practical implementation of this one, so that time you can definitely understand how to find C and how to find C star. Okay, so it's just a solution, like as we have discussed earlier, like our optimal solution is, so here C star is the optimal solution, like the cost of optimal solution. By the way, we must write that one. It's a cost of optimal solution is produced by the cost of optimal solution, and this rho is approximation ratio. Why we are finding that also we are going to discuss. Approximation ratio we should have to find out, like to say exactly how difference the approximation is behaving than the optimal one. So as we said, the optimal solution earlier in the graph which we discussed, just for an example, that time our optimal cost is 3, because 2 initially it was taking, then plus 1 is 3. This is our optimal cost. And the nearly optimal solution which is like which we got is 4. How to find then, like definitely the C is greater than C star we are getting. So you must write, like whenever we say the ratio, that time it is 4 by 3. Sometimes we are writing 3 by 4. Definitely 3 by 4 is less, because out of that we are finding the maximum. The maximum, definitely here we can expect the maximum 1 point something, which is definitely greater than the like 1, and that we will be discussing. So what is 1 and what is above that one. So here the maximum, the ratio whenever we find out is 1 point something we are getting as a ratio. Okay, the ratio is always needed. Why? Because how much greater value we are expecting than the optimal, that is why it is needed. Like if you are saying the approximation you are getting a 6, suppose your approximation is 6 instead of 4, that time you can say 6 by 3 or 3 by 6, so it is not able to consider, because maximum we are trying to find out. So here the approximation ratio is 2. If you're getting 2 and if I am getting 1 point something as approximation, then my approximation will be picked, then your approximation will be wrong at that sense, because the lesser towards 1 will be picked as a approximation, the best approximation. Though we know all are considered as approximation, even if you are getting, suppose you are getting 200 approximation, that time I must say it is an approximation for our solution. But one thing you should remember, 200 suppose you are getting, in other case if one person or might be anyone out of, like on the earth, suppose one person is there who found is 1.5 approximation, so his solution or her solution will be picked as the best approximation solution for the problem, and the best approximation solution is always being discussed. Okay, not your approximation solution. Might be your approximation solution is a solution, considered will be a solution, but effectiveness of his or her solution, which is 1.5, will be picked always. That is what the discussion of our ratio. Okay, that's why we are discussing about the ratio. Otherwise ratio will not be a vital role, because the ratio is exactly saying what is your effectiveness of the algorithm, or what is the approximation that you have already found out, whether it is effective or not. To distinguish the effectiveness, we introduce that ratio. Okay, so now coming towards this one, like that's why this formula is playing a vital role. We should have to know that one. As for the discussion earlier, like we discussed, like what's the minimization problem or maximization problem. Here the 2 points I mentioned here, like if C is less than equal to C star, okay, that time C star value will be more, means optimal solution will be more than the suppose in such case you got the answer, like here the optimal solution is 3 and your the approximation algorithm cost which you designed here is getting us 2. In that case, your approximation solution is the best solution rather than the optimal solution. That time what it is called as the maximization problem. Clear? That time it will be considered as maximization problem. But in general, minimization problem we are exactly expecting where it is sometime like we can say C is uh, greater than equal to C star. Here in general we are getting somehow towards the optimal. It is not always getting to less than the optimal. That's why we maximum time we are getting that one as this C divided by C star, or you can say C where C is greater than the C star. Okay. Now, I think you understood that maximization and minimization problem. Now we will go towards the one approximation algorithm. Okay. So here, nevertheless than one, we are discussing. So it will never less than one. Why we are saying that one approximation algorithm, whenever we are discussing one approximation algorithm, that one approximation algorithm is equivalent to optimal solution or optimal algorithm or optimal problem, you can say. One approximation is equivalent to optimal solution. Less than that is not exactly possible. That's why. Clear? So our main target is to find out the maximum here is exactly you can get whatever the value you're getting. That should be definitely okay. That should be definitely more than one or equivalent to one. Suppose you are getting one approximation, definitely you can say you're you are meeting with the target. Now optimal solution, suppose you are finding out here we are getting 4. If you are saying you one approximation, that time your solution is providing equivalent to the approximation algorithm. Then only you can say it is optimal solution or a one approximation solution. I hope it is clearly understood by you. Now we will discuss about the approximation scheme. Okay. So approximation scheme for an optimization problem. Optimization problem is all about to find a minimum or a maximum. Clear? A problem is an approximation algorithm that takes input size. In general, whenever we are taking the input size here, they are not exactly following the instance of a problem, but also value they have introduced as epsilon, which is definitely greater than 0, means you can start from 1 towards n. Okay. So another thing they have introduced which is fixed is epsilon. That time we can say 1 plus epsilon approximation algorithm. Okay. That scheme is called as polynomial time approximation scheme. Okay. As well as if you can say fully polynomial approximation scheme is what? I must tell you that one. Like whenever your input size is 1 by epsilon, which is the fixed size you have taken as a ratio, suppose you have added, as well as the input size is n. That time, the polynomial time it should run within the polynomial time. That's why we can say it's a fully polynomial time approximation scheme. There are two different type of schemes are available. One is polynomial time approximation scheme, another is fully polynomial time approximation scheme. For fully polynomial time, so we have to take 1 by epsilon as well as the input size should be the instance. Basically, whenever we have previously focused on the instance with the number of size, the size of the input, as well as one fixed portion we have added there, as we have done in space complexity. If you have remembered that one, we have added the auxiliary space. Here is some similar to that one. So like input space they have set as n. Here they introduce like 1 by epsilon. If those things are being incorporated, then we can set a fully polynomial time fully polynomial time uh, approximation algorithm. As well as suppose here we set a value is epsilon, which is fixed with the n input, then we can say the scheme is polynomial time approximation scheme, which is also named as the approximation algorithm is 1 plus epsilon approximation algorithm. Okay, so here is an example. It is they have taken like the time exactly the running time they have they found out like if such thing like big of 1 by epsilon square if n cube is there, so a constant factor they have introduced. Basically if epsilon is decreasing, based on that they can found out like it will be certain amount like they are getting with the polynomial time complexity. Okay, So I hope this is clearly understood by you, like what exactly the polynomial time exactly is, or like why we introduced the approximation algorithm, and what are the schemes in detail, like what is a row of n, why it is important, why the formula is too important for us to know, like how to say which is an effective approximation algorithm. I hope it is clearly understood by you. If any doubt, please comment below and have a good day.